Okay, so today we'll be talking about operational transconductance amplifiers, or OTAs. And we'll take an intuitive approach so we can see more clearly what's going on. So first, here is the circuit schematic for the LM13700, which is a very widely used operational transconductance amplifier. And let's first recall the Wilson current mirror, since it's widely used in the circuit schematic, and then we'll see why, because right now it doesn't look like it's very similar to what's going on in every stage, but we'll make it take a form that actually let us understand. So first, let's recall the simple model. So the simple model for BJTs. It's gonna look something like this. Base, emitter, collector. Remember, it's just two PN junctions, so it's just two diodes back to back. Correct. And you got base, emitter, and then collector. Right, but now as you can see here for Q2, the base and the collector are tied together, right? So let's redraw that and see what's going to happen. What's going to happen is that instead of having a transistor there, we can model it with just a diode. So it's gonna base, collector, emitter. It's going to look something like this. Correct. So now we can redraw the current mirror to take this form. So from this schematic, we go to something that looks like this, where our bias is just R1, is just the current setting resistor. Q1 remains the same. Q3 remains the same. The load remains in the same place, and now Q2 is replaced by a diode, where the base and the collectors are right here, and the emitter is a ground. Okay, so as we said before, we have the sinking current mirror, because the current is being synced into the current mirror. That's going to look like this. Now, what about the sourcing current mirror, where now you're going to have, instead of having PN junctions, you have NP junctions, because you are using PNP BJTs. Well, it's going to look the base and the collectors are tied together, so it's going to look a single diode drop from emitter to base and collector. So Q1 is just going to be equal to Q1. It's not going to change. The bias and resistor is going to remain the same. Q3 is going to remain equal, but now Q2 is going to change to D2, correct? Okay, so here's what we have. We have the sinking current mirror, we have the sourcing current mirror, and we got the circuit schematic. So now note the similarities between Q1, Q2, and D1 in the circuit schematic with the sinking current mirror. The only thing that is not there is our bias. Normally the OTA is used with a control voltage that is coming from a biasing resistor that's controlling the current. So you got V control, that is right here. So now the circuit is the same, correct? So we can note it there. So this is a sinking current mirror. And you're gonna have the current coming down this way, with I1 equal to I2. So let's rewrite that really quick. So first, Note that I1 is equal to I2, and we're gonna call that current, that's it's called the control current. It's gonna be called IABC. Here's another thing to note. So this is a differential pair. Q4 and Q5 are making up a differential pair. So let's rewrite that. Ignoring the linearizing diodes for now. Linearizing diodes are only used to keep BD, or the differential voltage, very small. So let's rewrite that. So this is what we got. Q5, and we're gonna label these currents as I4 and this one as I5. We know one thing for sure, that it is, and then this one as I bias. So we know one thing for sure, and it is that I bias is equal to I4 plus I5, correct? And then we also said that I bias is equal to IABC, so let's just remember about that, so we keep it consistent. It's equal to I4 plus I5. Now, from the fact that this is a differential pair, if we increase Vn, then VVE is going to increase, so VE is going to increase and I4 will increase. Further, if we increase BP, then VVN, VVE will increase and I5 will increase, correct? So let's rewrite that very quick. Increasing VVN increases I4. Increases I5. So let's relabel that. So we know that Q4 and Q5 still are making a differential pair, so we call it diff pair. Okay. So now the next question to ask will be, so let's ask that, will be, the question is going to be, what are Q6, Q7, and D4? If you look carefully, you will see that they are source and current mirror, with Q8 as the load. So let's note that. So this right here is the sourcing mirror, and this right here is the load. Next question to ask will be, so what are Q10 D6 and Q11. Again, what are Q10, D6 and Q11? Well, those are also source and current mirror. The Wilson type. So let's rewrite that. So now again the next question will be what is Q8, Q9 and D5. So and those are a sinking current mirror. So now big question is what do we really have here? So 6. So that'll be, what do we have here? That's the big question. So one thing to note is that the branch current that goes through Q5, or what we call I5, is getting mirrored by the combination of Q10, D6 and Q11, which are a sourcing current mirror like we indicated right here, correct? So what that means is that I11 is equal to I5. So what that means is that I11 is equal to I5. Further, we also know that I9 is equal to I7 is equal to I4. Why? Well, the current that goes through I4 to Q4, which is called I4, is getting mirrored, and then it's going through a Q8, and then that's further getting mirrored and going through the sinking current mirror. Yeah. That's the combination of Q8, Q9, and D5. And that's why we have I9 is equal to I7 equal to I4. So now the next logical question will be, well, and so what is I out? Just by some simple KCL, you're gonna have the I out is going to be equal to I11 minus I9, correct? But we also demonstrated just previously that I11 is equal to I5 and I9 is just equal to I4. So that's just going to simplify into I5 minus I4. Therefore, by just pure simple analysis, we realize that the current that comes out of the OTA is just proportional to the difference of the current that goes through Q5 minus the current that goes through Q4. Correct? So that's simple. So we took something that looked very complex and made it just the difference of two currents that we have control over, because they are controlled by BP and VN. And further, as we all see, ABC, or the bias current, also plays a big role. So now the next logical question is, well, what is the what's the role of IABC, or the biasing current? So what's the role of IABC? Well, IABC, or scaling, is changing IABC scales I4 and I5. Why? Because and I5. Why? Because remember that IABC is equal to I4 plus I5, right? Since you got the branch current, that's I4, I4 plus I5 at this node, it's going to be IABC. So that's the current that's coming down here. So IABC is equal to I4 plus I5. If we scale IABC, we scale I4 plus I4 and I5. So now we want to know what is I out, but we want to know what is I out in terms of BP and VN, since that's what we put in. So like that. So we want to know what is the I out in terms of BP and VN. I out is going to be equal to IABC times BP minus VN over T. So now let's look at this equation a little more in detail, and we will see that why is IABC here? Well, remember that I out, it was equal to I5 minus I4. But if we scale the bias current, then I4 and I5 scale as well, correct? So IABC scales the output current, correct? Alright, so now why do we have this T term here? That T is in reality just a PVT constant, or this is called a process voltage and temperature constant. And it is in volts. In order to make this expression looks like the ideal expression for an operational transconductance amplifier, we like to choose K, which is the variable that they use, as being equal to 1 over T. So with units of 1 over volts. So let's replace and rewrite. So I out is equal to IABC times K times BP minus VN. So let's go over the units. What are the units of this? This is going to be current, so it's going to be amps over volts, and this is going to be volts. Okay, so now let's recall the definition of transconductance. GM, which is transconductance, is equal to transconductance, which is equal to ampere over volts, equal to I over V. Right, you get a current at the output for an input voltage. Okay, so now let's replace that. So let's rewrite the equation that we had before. It's equal to K times I ABC times VP minus VN. And from this we can just really quick just see that this is just GM and this is VD. So GM is equal to K times I ABC, and therefore I out is equal to GM times BD, correct? And now let's recall the ideal OTA. So let's call the ideal OTA, which is going to be something that looks like this. So the symbol for an OTA, let's rewrite that a little better. It's going to be something that looks like this. Here you go, where you got, here is IABC. It's called the bias current. And then you got B plus, so this is BP. This is BN. And this is BD. And then you have I naught, the output current. And then we know that the expression from that, the one that you can find in the book, is just going to be I out is equal to GM times BD, with GN equal to IABC times K, RI is equal to infinity, and R naught is equal to infinity. So we got there. So we got there to the ideal OTA characteristics. And we were able to just divide that complicated circuit into just simpler little blocks.